Alright, our next section is section 5.2, which is using perpendicular bisectors. We're just going to do part of this notes today, and then we'll update our vocabulary on Thursday. So, a segment bisector intersects a segment at its midpoint. You guys know that. Anything that bisects cuts something into two equal parts. So then a segment, ray, line, or plane that is perpendicular to a segment at its midpoint is called a perpendicular bisector. So a point is equidistant from two figures if the point is the same in each figure. So points on the perpendicular bisector of a segment are equidistant from the segment's endpoints. So basically we have these two pictures here. A segment bisector, basically what's happening, and I'll have you guys construct these in class at some point, is you have this segment here. And then you have a point that's in the middle, so this part is equal to this part, and that point is P. And running through that P is another line that happens to be at a 90-degree angle with that original line. And you can see the triangle in there, and what ends up forming is this shape where, first of all, those two bisected segments, those are equal. And then even more so, these two segments are equal. So you can see you're going to be setting some equations equal to each other to solve for x and solve for distances that way. So theorem 5.2 is just about this perpendicular bisector. It says in a plane, if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So if CP is the perpendicular bisector of AB, then CA is equal to CB. The converse of this perpendicular bisector, so the converse is going to say that you have two equal parts, and so it must be a perpendicular bisector. So in a plane, if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So in this case, if DA is equal to DB, then D lies on the perpendicular bisector of AB. So if you remember from chapter 2, I think, in this first theorem, our hypothesis is that you have a segment bisector, and our conclusion is then that you have two equal segments. And in the converse, that means you switch the hypothesis and the conclusion. So it says if you have two equal segments, then you must have this perpendicular bisector. So it's just kind of a reminder of what a converse does. So example 1 here, if your notes are a little messed up, let's fill this in. So line BD is the perpendicular bisector of segment AC. We want to find AD. So BD is this line right here. It's the perpendicular bisector of this segment right here. So that means that this is 90 degrees, this segment's equal to that segment, and that segment is equal to that segment. So we can set up an equation with what we're given. We want to find AD, so it doesn't make sense to set these equal to each other. So let's set CD equal to AD. Actually, let me switch the order here so I don't go crazy. AD equal to CD. So then if you fill in those values, you have 5x equal to 3x plus 14. You can see maybe why I switched them. I like my x on the left, so minus 3x minus 3x. We end up with 2x equals 14. Divide both sides by 2. You get x equals 7. Now remember, this didn't ask us to solve for x. It asked us to find AD. So AD is equal to 5x. We now have said that x is 7, so we have AD equal to 5 times 7. So AD is equal to 35. Your Go Formative homework today, I don't think there's any where you stop at just solving for x. I think all of them you have to plug it back in. So that's kind of, I always say this, but the bread and butter of what we're going to do today in terms of solving for x and plugging it back in. But just so we're clear on some ideas here, let's answer example 2 as well. So it says in the diagram, WX is the perpendicular bisector of YZ. So this line with the double arrows is the bisector of this segment with no arrows. we want to know what segment lengths in the diagram are equal. So they've given us some. They gave us that these two are equal, so we can start with that. We'll say the diagram, I don't know why I capitalized diagram. The diagram shows that Vy is equal to Vz, which is equal to 25. But now we know that that's not the only equal length. So we're going to go ahead and say, so that's our first one. The second one, though, so remember this must be equal to that, right? Because this is a bisector. So we can say, make sure I get the order here, because because Wx bisects segment YZ, then XY is equal to XZ. So that takes care of those two segments. This one is shown. Our last one then, so we want to show that this one is equal to this one. So for this last one, we can say W is on the perpendicular bisector of YZ. So WY equals WZ by theorem 5.2. Alright, so that's showing that all three of those parts are equal. And we actually had three here because we had two triangles. So then the last question wants to know is V on WX. So this one's actually sort of intriguing. So it certainly looks like it is, right, if this continues onwards, but we want a more rigorous reason why that's true. So we can say because Vy is equal to Vz, V is equidistant from Y and Z. So by the converse of the perpendicular bisector theorem, V is on the perpendicular bisector of YZ, which, oops, it's a funny W, which is WX. So this is all we're going to do for today. Tomorrow I'll go on to our other vocabulary term from this section. But this should be enough for you to do your homework today.